Hello, everyone. Thank you for joining us for this webinar by our colleague and friend from University of Illinois at Urbana-Champaign, Dr. Shaloo Rakheja. And we are really thankful for her accepting to talk about this timely topic about computational devices and applications of 2D materials, especially with the huge interest nowadays in semiconductors manufacturing. We're really happy to hear her perspective about this interesting topic. And again, on behalf of Chicago State University and Center for Information Security Education Research, we're really thankful for what she would be sharing. The way we'll be doing, she will go over her presentation for around 45 minutes, and then we can open the door for questions. So we can conclude in 1 hour. And Shaloo, the floor is yours.
Perfect. Thank you, Musa, for that introduction, and welcome to my talk. So as Musa mentioned, I'm going to be talking about 2D materials, focusing a little bit on their devices and then quickly moving towards applications. Before I get started, I would like to thank all of our grant sponsors, NSF, DARPA, Department of Energy, ARPA-E, Air Force, Semiconductor Research Corporation. At Illinois, I'm part of 2 main research centers. The first is IMERSEC, which is our materials research center. And the second one is ASAP, which is an industry university consortium working on industry relevant problems. So before I start, I would like to talk a little bit about my background. So I'm a computational theorist. What that means is that I focus a lot on modeling things, writing mathematical equations that would describe the physics of how electrons move inside materials, how spins move inside materials, particularly trying to understand what are the limits and bottlenecks in improving the efficiency of applications in low power memory, logic, and RF communication. So my main studies are in transport. So I am a dynamics person, meaning anything that moves in the presence of external stimuli, I should be able to model it. We've been focusing on bulk and confined structures. A lot of my work is also in the very, very high frequency terahertz signal generation, and spin and magnetization dynamics is another focus. So to give you a breadth of the devices and materials that I worked on. So in terms of the materials, I've been looking at the traditional semiconductors like 3,5 and 3 nitrides, very wide bandgap semiconductors like gallium oxide and diamond. Diamond is particularly exciting because in the past, people have been thinking of using this material as a thermal conductor and a heat sink material for a number of emerging heterogeneous integration applications. So I am interested in some of those applications, but we have an ARPA-E project where we are looking at diamond's use for power electronics. We shine light on diamond and try to excite carriers, and then we try to understand the amount of power that can be generated through optically gating this material. And then we also work in a number of other different kinds of materials, which are topological insulators, group 14 materials, transition metal dichalcogenides, and all of the bottom ones are chromium oxide and manganese-based materials are actually antiferromagnets, not ferromagnets, but antiferromagnets. So that's another very exciting space to be. And again, as I said, I'm going to be talking about 2D materials today because we have a number of industry-sponsored projects in looking at 2D materials for end-of-the-roadmap devices. In terms of device structures, you can see a portfolio of the device structures that we've been working on, which not only include your traditional devices like FinFETs and EDSOI, but also includes a number of advanced devices, for example, the optically gated devices. There's a very exciting topic that I'm going to be talking about today, which is in reconfigurable computing, where 2D materials are really important. So I'll show you a configuration of a FET, which can be reconfigured post-fabrication, allowing us to camouflage the circuit functionality and, in fact, use it for logic locking. So that's a very new area of my research as well. And in terms of the computational methods, we develop most of the code that we use. We've developed it in-house. It's a custom code. We are also very familiar with commercial solvers. So we do have a number of, we do have expertise in using commercial solvers. So my talk today is going to be really pulling my work from the 2D and thin film ferroelectrics and reconfigurable devices. So as I said, I'm a computational theorist. I don't want to be building models just for the sake of models. I think it is important to understand what these models are going to be used for and how physically accurate these models are. So I tend to think of my group as being in this business of atoms to assemblies. We really try to start from the atomic first principles calculations, which is on the left over here. Let me see if I can try to use my laser pointer. Yeah. So, so we do a number of these first principle calculations, which provide input to these TCAD models. If you haven't heard the word TCAD, it stands for Technology Computer Aided Design. So what that does is if you have a transistor, you can simulate that transistor device. The first one is just materials modeling. The second one is actually device modeling. This is the part that I'm really interested in. I do both of these things, but the TCAD is the one which I'm very excited about. Once I have these models, I can actually utilize them to build something called a compact model. A compact model is written in a language like Verilog, which is industry standard. So somebody like a circuit designer can come and take your compact model and try to run circuit simulations, different kinds of circuit simulations, whether they are time domain, frequency domain. What then that allows you to do is it allows you to close the loop between technology and circuit, between device and circuit. So this idea, this premise of co-design is something that you can really realize with the help of this full stack modeling approaches. So again, to emphasize, I think our group really excels in doing atoms to assemblies. We can start from atomistic first principle simulations and go to the representations of entire packaged devices. And in the process of doing so, we learn a lot about the underlying issues, but I think a lot of that learning also happens on the side of how to build better computational methodologies. How do we utilize GPUs in our computational schemes so that we can accelerate the calculations that we're trying to perform? So now this brings me to the heart of my talk, which is 2D materials for future heterogeneous integration. So far, the semiconductor industry over the last 5 decades has benefited greatly from scaling the silicon transistor. However, as we're entering this less than 5 nanometer technology node, there are obvious challenges to scaling the silicon devices. One of the main challenges is that once we scale the length of your silicon transistor, it starts encountering short channel effects. There's a lot of power dissipation associated with that as well. And there's a lot of power dissipation associated with that. And what that means is when we scale the length of the transistor, we also have to scale the thickness of the silicon channel. And that means once we scale it, we start encountering a lot of interface-related scatterings of electrons, which degrades the mobility. In the case of 2D materials, they are atomically thin materials. So they are naturally, they naturally do not have any dangling bonds in the third dimension. So they can truly preserve the mobility of the devices down to the atomic limit, I should say, monolayer limit. So they could compete, or they could even be better than the silicon transistors for end of roadmap applications. But so far, I think they have been really used in more applications, which would include sensors. So these are different kinds of sensors, gas, chemical, biosensors. People have been using it for NEMS and MEMS approaches as well. I think graphene is very attractive for doing photo detection and modulation. And in fact, people have been using 2D materials for integrating with your traditional silicon photonics and silicon nitride waveguides. Now, in terms of other kinds of computing applications, I think both neuromorphic computing and quantum technologies can vastly benefit from the 2D materials, because these 2D materials have shown a memoristic behavior, which means that we can utilize them as non-volatile memory on the chip for on-chip sensor fusion. In fact, people have also done a lot of other kinds of devices with them, including physically unclonable functions and radio frequency switching. In terms of the quantum technologies, people have been building these Josephson junctions, quantum dot qubits, thinking about topological quantum computing. So the bottom line is that 2D materials are really exciting for the CMOS plus X integration applications, and perhaps even for front end of line transistors at the very advanced node. So it's really important for us to be able to do the research right now. Now, more than 100 materials, 2D materials, are experimentally accessible. However, nearly 2,000 2D materials have been theoretically predicted. So what that implies is that these 2D materials are one of the most attractive candidates for us to develop future computing applications. In terms of the family of 2D materials, here's a table of some commonly available 2D materials that my group has been working on. So we have, first of all, Xenes. These are simple monolayers of single element. So you can think of it as graphene. Silicene is one layer of silicon atoms. Germanium is one layer of germanium atoms, and so on. So we've been working on that as well. Then hexanes and fluorohexanes are derivatives of these hexenes. So graphene, for example, means that this is hydrogenated graphene, and fluorohexanes like fluorographene means that this is fluorinated graphene. Now, we also have these transition metal dichalcogenides. These are materials which pick up a metal from group 4, group 5, group 6 of the periodic table. So for example, it could be molybdenum, and then you combine it with a chalcogen. A chalcogen is an element like sulfur or selenium or tellurium. So you can build materials like molybdenum disulfide, tungsten disulfide, and so on. We also have semi-metal chalcogenides as well. So these are similar to the TMDs, except these are semi-metal in nature. Then we have other materials like MXenes, which are ternary compounds. And finally, we have these 2D insulators. So we have insulators like hexagonal boron nitride, which is a great example of a 2D insulator. From this broad family of 2D materials, we can recognize that despite having a similarity in terms of their structure, they do come with a number of different applications, simply because we can get semi-metals, we can get semiconductors, we can get insulators from 2D materials. What I haven't shown on this slide is that these 2D materials, some of them are superconductors, some of them are topological insulators, and so some of them can bring, for example, even ferromagnetic insulators. So some of them can bring really very rich structures and rich properties that we can utilize to build these new devices. Now, one of the advantages that people often tout for these 2D materials is the ability for us to stack these different materials on top of each other. 2D materials have very strong covalent bonds within the plane, but out of plane, they have van der Waals interactions. So these materials naturally do not have any issues related to the mismatch of the lattice between the different materials. So it gives us the possibility to integrate many different kinds of materials with very strange, sometimes electronic properties and even optical properties. This doesn't really happen in the case of 3D materials, because 3D materials do have lots of problems with interfaces. They develop dangling bonds, and they develop interfacial traps. So you can think of 2D materials as naturally passivated in the third dimension. So you can really put these materials on top of each other. I should also mention that there is very interesting science happening today in taking 2D materials. You take the first layer, but you rotate the second layer slightly from the first one. So that can give you something called Moire superlattices. This has been observed in the case of bilayer graphene. And there is a twist angle. You can twist it. There is it's called a magic angle. There's a twist angle where you can get superconducting bilayer graphene by just twisting the first layer and creating those Moire superlattices. And this has led to the emergence of a new field of research called twistronics, meaning twisting layers on top of each other, something that you absolutely cannot do with 3D materials, but you can do with 2D materials. My talk is going to focus on these very unique materials called transition metal dichalcogenides. These materials, as I mentioned earlier, you have a metal, which is M over here, and X stands for a chalcogen. So you are thinking of materials like MOS2, WS2, WSE2, and so on. These materials have a metal atom in between, and then you have the chalcogen on the top, chalcogen on the bottom. So it's pretty much like 3 layers in some sense. They come in many different structural configurations, as I've shown on the bottom. So we are not going to be focusing on the octahedron configuration. We are going to be focusing on the triangular prismatic configuration, which is the 2H configuration. What this means is that the material is semiconducting. This is the most commonly available and synthesizable polymorph of these materials. So that's exciting for us. And if we are working on 2H materials, these are semiconductors. Their band gap, I want to say, somewhere between 1 eV to about 2.3, 2.4 eV. So very nice space for us to be working on. So the first application that I want to focus on is the front end of line field effect transistors, right? As I mentioned, that these are attractive candidates to even replace silicon for end of the roadmap. Why? Because as we're making our silicon thinner and thinner, it's going to encounter lots of scatterings, degrade the carrier mobility, not a great option for us because you are going to compromise the performance of the device. And in that regard, can we do something with these field effect transistors? And so the question that my group has been answering so far is, can you improve the mobility and the performance of this device? The second one that we are going to be focusing on is a back-end of line technology. This is a Schottky barrier device. And you can see over here, it also employs a ferroelectric. The moment you start putting a ferroelectric, a good ferroelectric, you can be sure that you are also going to get non-volatile operation, meaning you do not need to keep the device powered on in order to save the state inside the device. So that's the beauty of this device. And what I'll demonstrate is that it can reconfigure its functionality between N-type transistor and P-type transistor. So what that means is after fabrication, you can literally control what the logic circuit is going to look like. Is it going to look like a subtractor, or is it going to look like an adder? Because it's the same layout for both of these logic circuits, except that you can access the polarity of the device through a control gate. In a normal silicon MOSFET, the polarity of the transistor is set during the fabrication phase, right? You cannot control it after you fabricated it. So it's pretty much set in stone. But for these devices, the polarity is actually not set in stone. You make the device and then you decide after fabrication whether this is going to behave like a positive or a negative polarity, right? So let me start with the first field effect transistor application. There are two flavors of these devices that people have been talking about. The first one is a back-gated 2D FET. As you can see, we've applied gate voltage to the backside of the device. And the second one is a dual gated transistor where you have a top gate and the bottom gate. The nice thing about this bottom device is that the layout of this device minimizes the overlap capacitances between the source and the gate and the drain and the gate. So it's very exciting. And the other thing is we can degenerately dope the regions underneath the source and drain to get really nice ohmic contacts. People have also considered replacing these degenerately doped regions with semi-metals, for example, graphene, as an example of creating those ohmic contacts. And I think one of my colleagues is working on this issue of making contacts to the 2D transistors very nice, because that is one of the weaknesses of this technology, where it does not compete very well with silicon. So the benefit of these is that with their atomically thin layers, we can apply a very small gate voltage to turn the device on and off, which is really great. So it can have better electrostatics. And then I think the mobility, the one that I'm going to focus on is the mobility. And because these are atomically thin, you're not really getting those interface scattering. So they're really great tunable properties. Why? Because we can stack all these different materials together, which creates a very rich band structure for you to utilize. And finally, and very, very importantly, these materials are mechanically flexible. So you can strain the materials. I think theoretically, it's been predicted that you can strain it up to 30% without breaking the material, because these materials can deform out of the plane to relax and to release that stress that they're feeling. Whereas if you want to strain a 3D material like silicon, the bonds are very rigid. So if you start to strain it, once it reaches a critical strength, which is very small, you will break the material. So for 2D materials, you can really control how much strain you're applying, and because of their flexibility and bendability, they are naturally it's very easy for us to apply strain levels up to 30%. Though experimentally, my colleagues have been able to apply up to 1%, plus minus 1% strain in these materials. And I should mention that there are lots of challenges in 2D materials related to, for example, how can we reproducibly synthesize these materials on a wafer scale, right? If we can't have a process that is wafer scale, we wouldn't be able to use it at the same cost as a silicon process. The second thing is, even though these materials are naturally passivated, they can have defects within the plane of the material. So how do we control those defects? And then, as I mentioned, contact resistance is a biggie for these materials, because if you can't optimize the contact resistance, you're not going to get a lot of current out of the device. And finally, some of these materials are not very stable in air. So those are some of the challenges that one has to address. Now, I want to focus on mobility. Why is mobility an important parameter for a transistor? It is important because the higher the mobility, typically you're going to get more current. If you get more current, you can switch the device faster. So that's really important. We need to be able to improve the carrier mobility to improve the transistor performance. If you look at 2D materials mobility, it's all over the map. It's literally, you can find papers that report mobility in the range of 0.1 to 300 centimeters square per volt second at room temperature. So this is a huge variability. From an experimental standpoint, we need to be able to develop processes where this parameter is tightly controlled. And on the theoretical front, we need to be able to understand how we can control this, not only control this parameter, but also optimize this parameter for getting the performance that we desire from these 2D material-based electronics. So the real question is, can we apply process-induced strain to these 2D materials, and can we get a more tightly controlled performance, better performance than this random map that I've shown over here? My colleagues at UIUC, Professor Van der Zande's group, has developed a method to apply process-induced strain in a very gradual and systematic manner. So as you see over here, this is a 2D material. What they do on this 2D material is they deposit a stressor layer. A stressor layer is a material like MgO or aluminum oxide. MgO typically applies tensile strain. Tensile strain is where you're really stretching the atoms. And if you think of aluminum oxide, that's compressive, so it brings the atoms closer to each other. They gradually increase the thickness, and for each thickness, they measure the properties of the material. Is the mobility getting better? Is the strain transfer good? Is the current density improving? And then they put more stressor, then they put more stressor. And so for each level of stress, they can measure this property. And this approach is really nice because it gives us very high quality data to calibrate our models to. Secondly, it also minimizes device-to-device variability because you are applying strain in the same device. It's not like you fabricate one device and another device and you apply strain differently to the two devices. That's exactly what people in the literature do. They just make several different devices with different strain levels, which means that they can't really predict anything systematically because there is a lot of device-to-device variability. So in our group, we have been developing this methodology to define carrier mobility in these 2D materials. In a 2D material, the carrier mobility will be limited by intrinsic factors and also by extrinsic factors. So this is a 2D material, really nice material, but it can interact with the oxide on the top and the bottom. So that's one extrinsic mechanism of scattering of electrons. It also has phonons inside the material. So that's an intrinsic method of scattering of electrons, which will limit mobility. So our goal is to develop a methodology, develop a computational methodology that can predict three things. It can predict what is my baseline mobility, which is this mu E naught or mu H naught. This is an N-type material in the middle and a P-type material on the right-hand side. Second thing we want to be able to predict is what is the enhancement. I apply a strain of, let's say, 0.25%, how much enhancement do I get? Do I get 25% enhancement, 50% enhancement, and so on? And the third metric that we want to evaluate is the rate of mobility enhancement versus strain. So these are three metrics that we need to really calibrate because these answer fundamentally different questions about our process. The first one tells me the baseline mobility, which is important to establish. The second metric tells me just how much enhancement I get by factoring out scattering strengths of different materials. So we can compare different materials. It's an apples to apples comparison. And the last metric is really a sensitivity metric. It tells me how robust is my application of strain, how robust is the mobility enhancement due to the application of strain, and is it going to be robust across different environmental factors? So we compute all of these three things. We have a methodology, which I'm not going to get into. This took about a year to establish because these are very heavy-duty calculations. But suffice it to say, once we implement this correctly, we can predict mobility as a function of strain, as a function of temperature, as a function of impurities, as a function of electron densities. And from that, we can figure out what is the enhancement and what is the rate of enhancement. So let me show you some results over here. We can see first we establish our intrinsic mobility of the materials at 0% strain. We can see that for most of the materials that we've looked at, which are listed over here, so we've looked at both molybdenum-based materials and tungsten-based materials. What we find is that intrinsically, the material can have mobilities in the range of 100 to 300 centimeters square per volt second. But when we include all of those interactions with your oxide layers and the charge impurities, the mobility drops by a factor of 10. Regardless, what I want to emphasize is that tungsten-based materials typically have a very high mobility. They have a mobility, I think the tungsten sulfide is an N-type material and tungsten selenide is a P-type material. So they have pretty good mobilities, I should say. And those are the ones I think are going to be really important as we try to build this roadmap for future electronics. So once we have our model, we try to validate the results against experimental measurements. So here we're looking at the measurement of the baseline mobility, which is evaluated at 0% strain. For N-type materials and P-type materials, the symbols over here are experimental samples, and the solid lines are the model predictions. And we can see that our model does a really good job at predicting a very broad class of materials across very broad temperature ranges, which is exciting. Not only that, we've been able to validate that our model predicts the experimental mobilities of these materials for different dielectric environments, which is also very exciting. So what I would like to emphasize is that within the expected experimental sample variations and environmental factors, our model is very robust because it is allowing us to calibrate it and predict the mobilities for a very diverse set of conditions. Okay, so that was my baseline. There is no strain so far. Now the question is, if I apply strain, what happens? The idea is pretty simple. If I apply strain to a material, its band structure changes. What is a band structure? It just tells me the electron energies inside the material for every momentum inside the material, for crystal momentum. So the idea is, if I can change band structure, then I can tune the carrier scatterings and I can tune the mobility. So that's exactly what we've done. A general trend of these materials is these materials have two valleys in the conduction band, meaning electrons typically want to stay in the lower energy state, but sometimes they can also get to the higher energy state. And that's what causes a lot of intervalley scatterings, and that limits the mobility of these materials. But when we apply strain, a general trend emerges. When we apply the right direction of strain, for N-type materials, if we apply tensile strain, I can move these valleys apart. If I move these valleys apart, then electrons will not have any incentive to go from one valley to the other valley. So that can increase mobility a whole lot because I'm preventing them from scattering from one valley to the other valley. On the other hand, if I have compressive strain, meaning I put the materials together, for a P-type material, the same story occurs, that we can prevent intervalley scatterings. And we've actually shown this through atomistic calculations that intervalley separation increases due to strain for all of the TMDs, which enhances their mobility. So this is the result that I want to really emphasize. For N-type materials, if you look at the orange shaded region, which is my positive direction of strain, this is my direction of tensile strain, and I can see that my mobility increases as my tensile strain is increasing. Now let's turn our attention to the middle graph, which is for P-type TMDs. And we can see that for P-type TMDs in the blue region, where I have negative strain or compressive strain, their mobility increases. So for N-type materials, if we want to improve their mobility, we really have to stretch them. For P-type materials, we have to compress them. And generally, it is very, very robust. We can see that the rate of mobility enhancement can be anywhere from 1.2 to 2.8x for most of the TMDs that we've studied in this in our research group. All right, so let me also show you how our results match up to the measurements. So we can see this range over here. The pink range over here is predicted by our models. And the symbols over here with their error bars represent the experimental investigations, some coming out of UIUC, some coming out of other places. And we can see that our model really captures the range of the mobility enhancement across MOS2 and WS2 very nicely. There is very little data available in the literature today for P-type materials. My hope sincerely is that our research can really guide the development of P-type materials and strain application to them so that we can develop a roadmap for future of P-type materials as well. Because as you know, for CMOS, we not only need N-type materials, we also need P-type materials because we want to be building complementary technologies, right? So that's one very important thing to remember. Suffice it to say that our model shows highly robust results. Now, I should mention, this is my last slide on strain, and I'll move on to my next topic. Process strain is not a new thing. If you look at your cell phones today, every single transistor inside your cell phone is strained intentionally. And industry has been applying intentional mechanical stress as far back as 2001, in fact, to improve the mobility. They do this by making the source strain embedded with germanium, which applies compressive strain to the P-type material, or they can apply a silicon nitride high-stress film to do a tensile strain. So this isn't new, and people have shown that this can really enhance the mobility of silicon transistors, both N-type and P-type. right? And in fact, I should mention that the research in straining of the band structure and then improving the mobility, I think that started in 1990. And then it took about 10 years for the industry to develop a process that they could really implement on wafer scale. And that was, I think, in 2001. And it's been 25 years now. And this is something that, routinely, we don't even know about it. But every freaking transistor that comes out of TSMC or Intel is intentionally strained to improve its performance. So can we do something similar with 2D materials? My research has shown that yes, strain is a versatile knob to improve mobility. Not only is it a versatile knob, it is a highly robust way to improve mobility because it is less sensitive to the environmental variations. So we can really work a little bit more on it to improve the performance of the 2D materials. Now, this also brings me nicely to my second part, right? For the first part, we really were focusing on performance. These are devices that hopefully will complement or replace silicon down the road. But for the second application over here is, it's a little bit different, right? It still utilizes our 2D materials, but now we want to answer the question, well, can we do something unique with these materials? Can we get new computing types out of these materials? And as an example, my group has shown that we can reconfigure the devices after fabrication. And this is important because we can use these devices for hardware security. We can use these devices for reconfigurable computing. We can use these for data stream processors. My group has also shown that we can implement content addressable memory or associative memory with very, very few transistors using these devices. So let me explain to you what happens in these devices and what makes them transform their functionality after they've been fabricated. So this is the semiconductor, right? The polarity of the charge carriers in the semiconductor determines whether this is N-type or P-type, right? So what we have done here, we've put a ferroelectric layer, and these are program gates embedded in the bottom of the ferroelectric. When we change the polarity, of the programming gates, it changes the polarization direction of the ferroelectric, so it can induce either electrons or holes in the device. So this is doping the semiconductor through program gates, through polarization of the ferroelectric material. It is not due to putting N plus or P plus dopants inside the material. So it's electrostatic doping, which is why we can control this. So now if we change the functionality of one transistor from N-type to P-type, what we can do is the same circuit can implement either a subtractor or an adder. We don't have to change the layout of anything. We just have to change the voltage on the programming gate. We have two programming gates on the bottom. And so what we've shown is that we have some work where we've shown that these can be really helpful for data stream processors, and we can do a lot of parallel processing on massive data for these devices. Now, let me show you again, this is an example of what is really happening. If we just focus on the direction from the programming gate, this direction, we can see that if we apply a positive voltage to the programming gate, then we can get negative charges in my semiconductor. When I apply a negative voltage to the programming gate, I can get positive charges inside my semiconductor. So I can change the polarity of these devices with the help of programming gate, and we've made measurements of the current as a function of the voltage. This is an optical micrograph of this device as well. So again, this is really exciting. And remember, this device is only changing its polarity between P-type and N-type. We have developed devices in our group where the device not only changes polarity between P-type and N-type, it can also implement memory on and memory off state. So it can implement 4 functions, and we've shown that with those 4 functions, we can implement for N inputs, we can implement all of the possible Boolean logic for N inputs using an N cross N array of these devices, which saves us a lot of area on the chip. So for a 2-mode operation, as I said, we can dope it entirely PP. So that's great. This is a P-type transistor. We can dope the device entirely N-type, which is this device. But what we can do, because we have 2 separate programming gates on the top, we can program one of the contacts as N, one of the contacts as P, or vice versa. We can program the left contact as P, and we can program the right contact as N. What the bottom 2 does is it gives us a diode. So we can really have a forward bias diode or a reverse bias diode, and it can have very interesting photo responses. So we've actually taken this device and we shine light and we see what kind of photo response we get out of this transistor by doping the source and drain differently. So our goal was to really develop this modeling framework. I will not get into a whole lot of details, but the basic idea for developing a modeling framework is that once we have this technology, we want to be able to utilize it in an architecture. And there are a lot of intermediate steps that we need to overcome. One is develop a physics-based model, implement it in Verilog A, do a circuit simulation, et cetera, et cetera. So for those purposes, we have developed a Verilog A model that captures the essential physics of these Schottky barrier devices. Remember, these are Schottky barrier. These are not ohmic contacts, because what we are doing is we're either injecting electrons or injecting holes from these drain or source through a Schottky contact that exists between the semiconductor and the contact. So these devices are not going to be as good as your front end of line transistors because their current is always going to be small. So that is one thing that we have to remember. And once we have our model, we can actually calibrate it with the measurements. So here are the device parameters, and our model, which is the solid line, shows a really good match with the experimental data, which is these circles over here. I should mention that when we fabricated these devices, there was a lot of leakage in the devices, and we could not really figure out why that massive leakage was happening. So in our model, we've only been able to calibrate the current minus the off current. So we're just assuming that the off current is 0 for these devices. And again, we've implemented this model in Verilog A to facilitate circuit simulations and circuit device co-design as well. So as an example, once we implement the model in Verilog A, we've been able to implement a content addressable memory. For those of you that are not familiar with how a CAM works, the way it works is usually in a typical memory, you give the address of the cell and you retrieve the data from the cell. Whereas a content addressable memory, you give the search. I want to search for the name, my name, Shaloo, in my dictionary. So then this memory will tell me all of the locations where my name is stored in the dictionary. So this is a really nice, it's kind of like associative memory. So it's useful for neuromorphic computing. And this is the circuit that we've implemented for a binary content addressable memory. Our 2D device is implemented over here. So first we store the data inside this through programming gates. Then we apply the search line voltage. If the search line matches with the program voltage, then we get a match. So for example, if my program is 1 and my search is 1, I get a match, which means that this path will turn on and my device will conduct the current. On the other hand, when SL is 0 and PL is 1, this device is cut off. So the way that the search operation is happening is it tries to match the data that I'm applying through the search line to the program voltage that I applied previously during the programming phase. And if there is a match, then it will discharge the match line over here. If the match line discharges, the output is 1. So when the output is 1, you know that there is a data match. When the output is 0, you know that there was a mismatch between the data. So we were able to simulate this circuit with the help of the Verilog A model that we've developed. These are the timing diagrams from cadence simulations, and we've also predicted the delay, energy, noise margin, and so on. I should mention that the circuit area is huge for this device because remember, this is a massive device that we just fabricated in our lab to demonstrate proof of concept. This is not the final version. This is not a mature technology. So we are really working hard to reduce the voltages. So you can see that the search line voltage goes between +5 and -5. That's not really ideal. We want to be able to search within 0 to 1 volt, which is compatible with the silicon technology. The circuit area is 50 microns. It's huge. So we want to be working on scaling this device. In fact, we have a paper coming out hopefully soon, which talks about if we did scale this RFET, how much benefit we would get. We've also implemented a ternary content addressable memory using these devices. A ternary content addressable memory is very similar to the binary CAM, except that it also affords the flexibility to have a don't care option. So for example, I want to search for all names in my dictionary that begin with SHA, and they are 6 letters long. So then my dictionary will search everywhere and it'll give me the location of all the cells where it finds the name that starts with an SHA, and it doesn't care about the rest of the data that's stored over there, right? So we need a don't care option. To implement this, we have 2 of my reconfigurable devices over here. And again, the programming gates are used for programming the state. So again, if we want a match operation, I will program both of these as 1. If I want to have a mismatch, then I will, or I should say, logic 0, then I'm going to program them as 0. If I want a don't care, then I'm going to program one as 1, the other one is 0, and so on and so forth. Pretty similar. Now, I think once we had our setup, I think this was an industry-sponsored project. They asked us, they said, well, you're doing all of this, it's all great, but what about the device-to-device variability? What about all of these variabilities that exist in your RFETs? So we decided to do a process variability setup, because process variability, controlling it is really critical, because otherwise you're going to have yield issues, you're going to have cost issues with your circuits. So we implemented a Monte Carlo simulation to figure out what the distribution of the search energy and the search delay would look like for given process variation. So these are the process variation inputs. Our Monte Carlo simulation runs. It predicts the output distribution. The output distribution is the distribution of energy, the distribution of delay. The parameters that we are varying are the supply voltage. In fact, supply voltage variations are number one cause of the variations that you're going to see in your circuit performance. We are also varying Schottky barrier height of the device. We're varying the dielectric thicknesses and the channel thickness of the material. So these are all process related, because I might have a process where I wanted to make thickness of 10 nanometers, but I ended up making it 9 nanometers or 11 nanometers, right? So it's really important to understand what that thickness variation would entail. So we did, I'm only showing the results of process variability for the power supply variability and channel thickness. What I want you to observe is, if you go to this part, you can see that my distributions don't look very Gaussian. Even though my input distribution for the power supply was Gaussian, my output distributions do not look very Gaussian. And the reason is that power supply has a non-linear impact on the circuit behavior. That is why you're seeing that. On the other hand, for channel thickness, you see pretty Gaussian performance. This Monte Carlo was implemented for 5,000 runs. So it's not as clean as you might expect. We do have some of the statistical issues that happen with small sizes of these runs as well. All right, so we've calibrated our process variability studies in this one table. I think industry loves tables. So we said, okay, we're going to put all of our analysis in one table. So these are the things we've varied. We varied the supply voltage, we varied the thickness, we varied the dielectric thickness and Schottky barrier height. And here we're calibrating the mean and the standard deviation of our output variables. Our output variables are delay and energy. We're doing this for all of the cases for the TCAM, match 1, match 0, and match X. I want you to notice that the variation in the Schottky barrier height results in the largest standard deviation in both the energy and delay. So controlling the Schottky barrier height is really critical. We also noticed that dielectric thickness can have a big impact on the search delay variability. So controlling that would be important for search delay, not so much important for energy, because it's not impacting my energy so much. And finally, supply voltage is a big impact in search energy variability. There's no surprise there. Voltage really determines the energy. So if I'm having variability in my supply voltage, that's going to have a big impact on my energy variability. As I promised you, we've developed a 4-mode device as well. The only difference between the previous version of my device and this device is that we have embedded a floating gate at the bottom. Everything else is the same, except I have a floating gate over here. So what that allows me to do is control the threshold voltage of the device. So I can have 4 different operations. I can have NFET, BFET, memory on, and memory off. And we can implement with this new device, I can implement my ternary cam with a single device. If you look at my ternary cam here, when I go back here, I need 2 devices, 2 of these RFETs to implement my ternary cam. But now with my 4-mode operation, I can do that in 1 device. So that's really exciting. It saves us a lot of area. And this is really the punchline of my talk for this 4-mode operation, is that oftentimes we want to build these lookup tables, which is a very critical component of FPGAs, the field programmable gate arrays. The way one does it is using either a CMOS decoder or a CMOS multiplexer. So for a 2-input CMOS decoder lookup table, we need 52 transistors. For a CMOS multiplexer, we need 30 transistors. With a 2-mode device, we'll need 12 transistors, and our 4-mode design, 8 transistors. So we are saving a lot of area with this. In fact, the area savings are about 3.4x. I should mention this circuit over here. This is a 2x2 lookup table. So we have 2x2 array in the top, 2x2 array in the pull down. If I, instead of using 2x2 array in the top, if I used n by n array, what I can do is I can generate all possible Boolean logic operations with this array. 2 to the n functions can be done. Don't have to fabricate this separately for each function, right? So that's the beauty of this. The layout is exactly the same, and you can change the functionality on the fly. And this is a topic on hardware security that I'm working with my colleagues from Texas A&M. They are looking at this reconfigurable circuit using these devices that goes between logic 1 and logic 2. And they have been able to show that this is going to be much more area efficient, energy efficient for doing actual computations. We are developing a methodology for synthesizing large scale circuits with this, because right now we've been doing this on pen and paper and literally just saying, oh, we want to build a subtractor, let's do it. We want to do this. But what if we want to do a big synthesis of something very, very complicated? We won't be able to do it just by pen and paper. So we need to develop a EDA methodology, which, you know, people have, we have EDA methodologies for decades now for CMOS, which has been really successful in pushing the technology forward. So we want to be able to do something similar for reconfigurable circuits. My last slide. There are a lot of other applications in spintronics. Spintronics is a really, really exciting field of study, because what we can do with spintronics is not only uncover some fundamental physics, but we can develop useful practical devices such as spin torque memory, which can be integrated as an embedded memory with silicon, maybe as L3 cache or L4. It hasn't happened, but hopefully it can happen in the future. And I think it's also very exciting to know that there are a number of companies that provide standalone chips of STT memories. So with these 2D materials, my hope is that right now, all of those memories are based on very traditional magnets. So think of cobalt, iron, boron. That's what they use. It's a 3D material, great. But I think with 2D materials, we can really improve efficiency, which is really important. So we can reduce the energy consumption as well. Besides, I think the physics of electron and spin is so rich that this is just an exciting area to be working on. With this, I come to my last slide. What I hopefully have emphasized today is that 2D materials are great. They can have lots of interesting science. One of the benefits of 2D materials is that you can stack them without having any issues at the interfaces, because they are naturally passivated in the third dimension. We can build a number of photonic devices and electronic devices with them. Beyond that, people have been thinking of sensors because they have a very big surface to volume ratio, and you can functionalize them. What that means is that you can attach a molecule to the surface of the material and it changes, for example, the current conduction property. So you can detect the molecule that is attached over there. And don't take my word for it. This is a very, very fast growing area of research. In 2004, you had just about under 2,000 papers that were published. And I think in 2021, when I looked at it, it was about 49,000 papers. I haven't done in the last 4 years. So this could have very easily doubled or something. I should probably put that on a chart and develop a Moore's law relationship like that. I should do that. I haven't sat down to do that. What I hopefully, I think when I work on a lot of industry-sponsored research. So one of the things that I want to emphasize from an industry standpoint, and this, I think there's a really nice article called 20 Years of 2D Materials, where they say that, 2D materials are great. There's a lot of fundamental physics problems to solve. But I think the biggest challenge today in our industry is, how do we actually make them useful for society? None of our cell phones are coming with 2D materials. Even the Internet of Things devices, my fridge is a smart fridge today, and I don't know what else is smart today, but they are not coming with 2D materials. So how do we as a community work on things that can take these novel research ideas and put it into practice? Selfishly, as a professor, I want to focus on fundamentals. I have no interest in doing commercialization of the technology, but I think that that's what's missing in the community. I think we ought to be thinking more seriously about it. With that, I will stop sharing, and thank you for listening to my talk.
Thank you so much, Shaloo. It's really, really amazing. I really appreciate everything you said. You raised many, many points, and your last words summarize it all in my mind, because I was really thinking about the application aspect of it. And but it's really hard, as you said, going from theory to practice is really hard. But hopefully we will get there with the many nice features you mentioned about these materials. But let me ask a very quick question about, again, it's very basic question, which is what are really the 3D materials is very easy to understand, but the 2D materials in semiconductors, as far as really the key differences between them is just a dimensionality aspect, or
Yes. Yeah. So there are 2D materials that can have other interesting properties, which I don't want to get into, but on a very simple level, think of stripping away all of the layers of silicon bulk and extracting a single layer out of it. So that becomes, in the monolayer limit, it's a 2D material. The thing with the 2D materials, with the ones that I'm talking about, not all 2D materials are like that. They have very strong bond within the plane. They're very strongly connected. But out of the plane, if you want to put another layer on top of it, they have very weak interactions. So there can be a lot of slippage. There can be a lot of other things. So these weak perpendicular forces and strong in-plane forces gives very interesting physics. So graphene is not at all like a semiconductor, right? It's a semi-metal. Not only that, it's a Dirac semi-metal. So I should say on some level, yep, you can think of them as just a 3D material in the 2D monolayer limit. But it can also look very different. Just from an electronic structure standpoint, it could be very different. Yeah.
Okay, thank you. Any question from the audience? See Dr. Archie, or for some reason, if you are talking about not hearing you. Maybe I can have one more question in my mind before until they get the mics working. Is a fact, I read some of your work about the connection between AI and semiconductors and material science. And nowadays with digital twin, how do you see this connected to this movement as far as, and also now we have quantum as the key word.
Yeah. Yeah, there's also something called quantum AI, by the way, if you haven't heard of it, quantum ML and quantum AI, which anyway, I think, see, for AI, we need a lot of hardware to do computation, right? We have these big server farms where we are sending our data and it's doing all kinds of calculations. It's really hard to do AI calculations on your cell phone. We can't do them. So I think one of my hope is that the connection point is that let's try to develop technologies for edge computing or Internet of Things using these materials, because these materials are lightweight, low cost, easy to integrate, and some new functionalities. They might not have the performance that is needed for the server farms, but surely they can be used at very low energy, low size for edge computing applications where you want to simply deploy this in a remote environment and let it sense things, do on-chip sensor fusion and things like that. So that's a very nice connecting point. I don't imagine that NVIDIA will come and tell us any day soon, hey, let's replace silicon in our GPUs with 2D materials. That's not happening. So let's not worry about it. But what can happen is in this space, in this really nice space of edge computing applications. And the other thing that I see with these 2D materials is providing support for back end of line. So if you think of monolithic systems, we can think of very high performance transistors integrated in the front. And then at the back, you can have some sensors implemented with these 2D materials, which do not need to have the same performance. And they can simply work alongside silicon, and we don't have to use silicon to do the back end. So some stuff like that could be very helpful.
But did you actually, I was also thinking about the other side of it, like using AI for the discovery phase about the interactions between these materials. And so you can have because the characteristics of the materials you were describing, it's very tricky, and the sensitivity of the materials themselves is also tricky. How did you, if you're not sure if AI can be helped somewhere there?
Yeah, I think in terms of materials discovery, AI has been used a lot. So for example, when we do these first principles calculations, we have to accelerate them, and we can use AI for discovering. But a lot of the times, what I've noticed is, as I said, people have been predicting materials left and right. Periodic table is yay much. If you combine everything together, you can imagine the number of compounds that we can get out of that periodic table. So while AI has been great in making some predictions, I think We still need a lot of physics-based understanding, which AI obviously cannot provide. It cannot tell me the reason behind, for example, how these atomic orbitals overlapped and why did this physics emerge from that. It can tell me, yes, this physics emerged, but it can't really tell me why that happened. So I think there's a lot that the AI still needs to learn. On the digital twin side, I think for now, it'll be the opposite. I think right now, the experimental and physics people have to provide a lot of data to the digital twin for it to even start processing it and understanding what we are supposed to be doing. So I think it's really far away for me. And these are very, I should say, very tailored things, right? Every process is very, very tailored. So developing a general digital twin, I think it's very, very far off. So we are not using any digital twins. We're not even providing data to our digital twins. We are using AI for materials, materials modeling. We are, so not any digital twin.
There's one, I think we have room for one more final question. There's a question from Archie saying, how do you see some of these ideas integrated into some of our courses to prepare students for industry?
I mean, that's a really, really hard question, right? I can answer from UIUC perspective. The way we've been tackling this is faculty will often develop courses or special topics that's very well aligned with their research. So we do have a course called 2D materials on our roster, and it's a permanent course now. So we've been doing that. And I think the best way that has worked for me and many of my colleagues is to absorb undergrads in our research groups and have them work on industry-facing topics. So don't keep them on some very bookish knowledge. I think they should be trained to communicate their research results to industry from a very early standpoint, so that it's like almost like a very immersive experience for them to be working alongside grad students, working alongside faculty, breaking things, understanding what's happening. So that's important. In terms of courses, I think that's really a very departmental college issue. We've addressed some of it. We're not the best by any means, so still a big learning process for us.
I'm muted. Thank you so much. I really appreciate it. Now this takes us to the end of the webinar. Again, we are really thankful on behalf of Chicago State and the team here. You're giving us 1 hour of your time with this very busy time of the semester. It means a lot to us. Thank you so much for your time and for the insightful things that you shared with us. And we'll connect with you soon.
Yeah, thanks everyone.
Thank you so much.
Yeah, bye.